Okay, well, in his introduction, Nigel emphasised the enormous breadth of Michael Atiyah's research interests, mathematical interests, ranged from geometry all the way to physics. And that's very much, that unity of perspective is very much exemplified in the work of Minhyong Kim, whose interests range from arithmetic geometry through to physics. And I think we're very grateful to Minhyong to come and give a talk today, and he's going to tell us about index theory and gauge theory in arithmetic geometry. Minhyong.
Thank you very much for the introduction, and thank you to the committee for inviting me to speak here. I didn't know Michael Atiyah at all well compared to many people here in the audience. However, his mathematics really did influence my development as a mathematician profoundly, I think. And I've written about this in an obituary I wrote for the newsletter of the LMS that came out in March of last year. So anybody who's interested in personal reflection can check there. I also described there how I did end up speaking to him a great deal during the last 3 years of his life. Was really fortunate, regard myself as very fortunate to be able to have had some contact with the vitality of the vision that he conveyed to anybody who met him. So since, as John mentioned, the conference is supposed to be about the unity of mathematics, I chose my title to convey the idea a little bit, and also because I thought this combination might be a little bit surprising to many mathematicians. But my main point is it shouldn't be. Actually, most of what I'm going to speak about today is very well known, this impact of index theory and gauge theory. I'll try to include also here and there some original contributions, but mostly it will be a survey of well-known material of the sort that I hope Michael Atiyah might have enjoyed listening to. They had it in here. So this is a very brief plan. It's okay if we don't really get all the way through the material because.
Minhyong, can you speak up, please, a little bit? It's very hard to hear at the back.
I was about to say it's okay if we don't get through the material. It's designed to be somewhat modular. The choice of topics here. So I'll start out at the beginning with a discussion of the index theorem, which after all is Michael Atiyah's most well-known work, and its relation to metrized vector bundles. So I'll start out with this setting, which is familiar in algebraic number theory. You'll have F denotes an algebraic number field, and it has a ring of integers in it. And a metrized vector bundle in this setting is a rather obvious object. It's a vector bundle on the spectrum of the ring of integers together with metrics at Archimedean completion. So this is an object that comes up here and there in number theory, in arithmetic geometry. Sorry if there's a lot of notation up there. This is just a projector, a locally free OF module of finite rank, together with a Hermitian metric whenever you tensor this module with R or C. That's the idea. That's what a metrized vector bundle is on a ring of integers. So it takes a while to motivate why this is a natural thing to study, but there's a philosophical reason, for example, that if, there's this point of view that in arithmetic geometry, the spectrum of a ring like O of F corresponds to the prime ideals. So this is, by definition, as I said, it's the set of prime ideals, but it also corresponds to equivalence classes of non-Archimedean absolute values on the field. That's one way of thinking about this integer, this spectrum as being identified with absolute values. So that if we allow Archimedean absolute values as part of the set, people like to sometimes think of this as a compactification of the spectrum. So it's like the relation between A1 and P1, affine space and projective space. So somehow considering a metrized vector bundle is very much like extending a vector bundle to the compactification. And from that point of view, putting a metric on these things, therefore, really is like an integral structure at infinity. So maybe I was going to explain a little bit more about that, but I'll probably skip that. So there's a way, I had a few lines here explaining how the integral structure is like a metric. Maybe it's best to read if you're interested later in the slide. But also, you see, I also wanted to mention the other concrete perspective whereby things like this arise naturally. That a metrized vector bundle when F is just a rational field, it's just a free abelian group set to the M together with a metric and the real tensoring with R. So this you might In other words, it's a metrized lattice, so you might believe that that's a natural object in arithmetic geometry. Remember. Now, the basic object regarding these metrized vector bundles that we like to study is the set of global sections. Right? And the set of global sections is just really just a pointed set. It's actually not a vector space or an abelian group or anything, because you're looking at the global section of the bundle without the metric, but requiring that you're only looking at the section. You're requiring the sections to have norm at most 1 for all the Archimedean absolute. So that's just a set. You can't add or anything like that, something like that, right? So you have a pointed set which defines the set of global sections of a metrized vector bundle, the ring of integers of a number field. And we might ask, when is this non-zero? Of course, you always have the 0 section, which is the point, referred to in the pointed set business, right? But when do you have actual non-zero sections that have norm less than 1 everywhere? So maybe I'll give you the basic examples that come up. Well, an example or a family of examples whereby such metrized vector bundles come up in number theoretical problems. So the typical situation is, so this is describing, in some sense, the simplest non-trivial situation of this sort, where you have a family of curves over the ring of integers. So in other words, you can just consider this to be a bunch of equations with integer coefficients, right? So if you have a family of curves like this, and then, of course, associated to such a family, you have the relative differential forms, which define a line bundle on this family. You have to modify it a little bit to turn it into a line bundle because the family may have singularities. So all these so-called relative dualizing sheaves, but essentially it's the ring of relative, it's the module of relative differentials. So if you take an object like this, then its global sections will be a module over the base ring, right? So this is the algebraic vector bundle without metric. But of course, if you consider the complex or real points of this algebraic curve, you also have L2 inner products on these bases. So these kinds of global sections in the usual algebraic sense, coming from a family of curves, actually naturally carries L2 inner products when you consider what happens. So this is a typical example of a metrized vector bundle. So the search for global sections really just becomes that of trying to find an integral differential form on this curve that has L2 norm less than 1 everywhere. So they may exist or they may not, but anyways, so you can imagine what can happen if you try to make the coefficients of the differential form integral, the L2 inner product might increase. If you try to make it smaller than the L2 inner product, well, it will become non-integral. So this is the kind of balancing act between requirements of integrality at finite places and small norm at infinite places that come up when you study these differential forms. Or you might put some more condition on it, like looking at the differential forms that vanish at a point, in which case you're looking at an integral differential form of small norm that furthermore vanishes at a point. And consider variations on conditions of this sort. As always, you might be able to imagine anyways come up in number theoretical problems. So how does one deal with this question of existence of points? So there's a kind of Riemann-Roch theorem, which I think is due to Arithmetic from the early 1970s, where given a metrized vector bundle of rank m, you take the top exterior power, then you get a metrized line bundle, and it's possible to define its degree the same way you would do it for a line bundle on a Riemann surface, for example, on a complex Riemann surface. You choose a section, right, a non-zero section, and take the log of the absolute values with respect to all the absolute values, including the Archimedean and the non-Archimedean. To do this, remember the non-Archimedean absolute values corresponding to the integral structure. So that all makes sense. And that formula is independent of the choice of sections because of the product formula involving all the absolute values, the full set of absolute values. So when you do this, you get a notion of a degree of a metrized vector bundle. There's also a notion of an Euler characteristic that's just defined to be the co-volume inside the vector bundle tensor with R. So you get a real vector space when you tensor with R. M defines a lattice inside here, and since we had metrics everywhere, it makes sense to discuss volume. So that's the definition of the Euler characteristic. And Arakelov, which proved a Riemann-Roch theorem of the sort, And you see in the theory of Riemann surfaces involving the Euler characteristic, the degree, and the Euler characteristic of the ring of it's usual absolute value. So this is actually relatively easy to prove, but it's an interesting formula. And in fact, the Euler characteristic of OF itself becomes also a very natural arithmetic invariant. It's essentially the log of the square root of the discriminant of the number. That's what you get when you compute the Euler characteristic of three formulas. And of course, you get an obvious fact. Well, it's not quite obvious, actually, sorry, a natural fact, but it's not obvious. The fact is that if the degree is larger than minus n times the Euler characteristic of the number field itself, or the ring of integers itself, similar again to Riemann surfaces, and in fact, this H0, these global sections that have a norm less than 1 at all large and medium places, in fact, is non-zero. You get non-zero small sections if you impose this degree condition. And I said that it's natural because it looks natural from the point of view of Riemann surface theory, but it's not so obvious because this is actually a reformulation of this theorem of Minkowski that many of you may have seen about convex bodies, convex symmetric bodies in Euclidean space, and when does it contain a lattice point? You have a lattice, you have a convex and symmetric body, and it contains a lattice point if its volume is sufficiently large compared to the volume of the lattice. This is a reformulation of the fact that you have a section of small norm for this metric. So that's a Riemann-Roch theorem that applies in this context. So this may already point you a little bit in the direction of index theory, since index theory. The index theorem, of course, is a grand generalization of Riemann-Roch theorem for Riemann. All probably so in fact, I'll take you right away then into a more sophisticated version connection with the index theory, whereby you consider a relative Riemann-Roch theorem of exactly the same kind of flavor. So now we have a family of curves that is, as in the example I showed you earlier, a proper regular flat morphism, which is a family of curves indexed by the ring of integers, this number field. And you can formulate a natural notion of a metrized vector bundle on this family. So that's again a similar or a metrized line. Well, you can do a vector bundle. Well, I just discussed the case of a line bundle for simplicity. But it's just a vector bundle or a line bundle in the usual sense on the scheme C. But you put metrics on all the base chains, on all the complex points. Family defined over. Now, when you start with this kind of doctrine, so here's the relative Riemann-Roch theorem. So I'll just tell you the form of it and try to give you some sense of what it's about. So it says that you should take the determinant of homology of this line bundle, right, and take its 12th power is isomorphic to some other line bundle. Right? But the point is, so in this form, just the algebraic form of it is the Grothendieck-Riemann-Roch theorem. So this was a version of many similar theorems proved by Grothendieck quite a long time ago. But what out of this work of Arakawa was developed in the 1980s, the version of this where both sides are equipped with metrics. So this becomes a metric isomorphism for this line bundle over spectrum. So the version I'm telling you right now was proved by Deligne. And what he did was he defined intersections and numbers and all of these things of this sort as line bundles on OF rather than just numbers. He sort of elevated usual numbers into line bundles, right? So that you get a metric isomorphism whose degrees will give you things that look much more like usual. But now, so here's where you'll see the more direct connection to index theory. When I spoke about this being isomorphism of metrized line bundles, and the metric on the left is the one that's defined by Cullen using regularized determinants. So there's a metric on determinant line bundles involving regularized determinants of Laplacians associated to the d-bar operator on that. You can use that to define a smooth metric on manifolds and line bundles of this sort. And in fact, what Deligne did, he showed you how to define natural metrics on the right-hand side as well using Green's functions in such a way that this becomes a metric. And in fact, this is a local index theorem. You might call this a very local index theorem. So in what sense? You see, what happens is that this is for a single curve, but you can do this for any family of curves, right? A sorry, I forgot to say, in fact, you can imagine you might be able to use a theorem of this sort to compute Euler characteristics and or compute degrees and apply to the existence of sections of small norm. But in any case, the formula actually holds for any family of curves. In fact, for the universal family of curves over the moduli stack of curves for genus P. You can prove this without geometric isomorphism over this universal family. And now, when you differentiate the metric isomorphism, what you get is the local index theorem of Quillen. That was also, I mean, you can prove it for other kinds of operators, in particular the Dirac operator as well, right? Which becomes an equality of differential forms. But this index theorem lifts it to an isometry between line bundles, such that when you take dd bar log of section, you get the differential form index theorem. That was proved by many people, starting with the so that's the sense in which this metric isomorphism you can view as being a very local index theorem. It even makes sense at a point, and it implies any of the other index theorems. In families or after the. So this is kind of, so I should say, so this was known in the 1980s and generalized and developed by many people. I'll just say a very few words about why these things arose and how they may have been applied. You see, what happened is that if you took actually a point of a family of curves like this, and you pulled back a metrized line bundle on the curve, to a metrized line bundle on the number fields, right? Then by taking the degree of such a pullback line bundle and regarding it as a function of the point, you get one of these things, the number theory is called height function. You can prove finiteness of points by showing that the height of points is bounded. So that's a typical approach to proving finiteness, which is very old, but this gives a kind of geometric interpretation of this height function, which allows you to do all the things that high natural geometric intuition. And of course, Atiyah likes to geometrize everything, so he made like this construction very much. I didn't really ask him about it. But meanwhile, also, if you take the degree of determinant homology rather than for pullback by a point, this can be regarded as a height of the curve itself when you regard it as a point inside the moduli structure. And this construction is also very important in the approach to the model conjecture by people like Hawkins and Voigt. This is just a very brief picture of how one might use it. Somebody's painting a picture of that on the slide. Or rather, somebody's young child is probably attending together. Yeah. Anyway, okay. So let me move on to a very brief discussion of gauge theory, right? So what I'm about to describe right now is certainly has nothing to do with my own work, I couldn't resist saying something about it because, of course, this was very important. This is a very important part of arithmetic gauge theory of some sort, almost for my generation of mathematicians. Right? So this is the study of moduli spaces of Galois representations. I'm referring to this theory that I'm about to describe right now as kind of a pre-gauge theory for a reason that will become apparent. Okay? So here, what you do is you start with the same kind of ring of integers of a number field, but you remove a finite set of primes, typically, right? And take the fundamental group of that spectrum. So this fundamental group approach is, or terminology and philosophy is very important, but in classical algebraic number theory, this is typically what you call a restricted ramification Galois group. You take the Galois group of the algebraic closure, right, but only allow those field extensions that are ramified outside, unramified outside the set of points. Right? So this is a restricted ramification Galois groups, and then you're interested in studying representations, continuous representations of this group into the points of an algebraic group, for example. So this is a very old object of study in some form or another. For example, E may be an elliptic curve. You can start out with an elliptic curve that has the reduction outside this set of prime test, right? And then if you take the p torsion of that elliptic curve as a group, it will be just fp squared, just a two-dimensional vector space over the finite field fp, right? So, but of course, because the elliptic curve is defined over f, it admits an action of this Galois group. So you get a representation from pi sub s to GL2 of fp. So this is an example of a Galois representation where f On the other hand, it's also quite important to allow this limit. You take the limit over all p power torsion points. If you do that, this is sometimes called the p-adic state module of the elliptic curve. It becomes isomorphic as a topological group to Zp, the p-adic integer square. It's a rank 2 module of the p-adic integers, but it still admits an action of the Galois group. And so you get a representation into GL2 of Zp. I guess I've denoted here by rho sub e comma ep and rho sub e comma zp. But this representation can be viewed as lifting or deforming the representation on the p portion, right? Because Zp has Fp as a portion, as a residue ring, and this representation is somehow lifting. So viewing this in a geometric way, right, as kind of a formal deformation of this representation over a finite field was very important for a number of different developments in arithmetic geometry since the 1980s. So, for example, Baring Mazur initiated this study that's sometimes called the deformation theory of color representation. It sort of makes this whole picture abstract, right? Axiomatized the thing, where you very generally can look at representation into points of algebraic groups in finite fields, right? And see how you can lift it to rings that have this little k as a residue ring, like in our previous picture. For example, it might be Zp going to Fp, or it might be some large power series ring over Zp mapping to Fp. You might be able to construct large families of Galois representations that form a tiny Galois representation. So he started studying these things from kind of geometric moduli space point of view. And then notice that you can also form a category of these things. So if you have two rings, A1 mapping to A2 mapping to the little k, so that both of these are rings that deform little k, then you can study diagrams of representation. And we call those as coming together from a category of deformation. So, for example, you may have a picture like that, right? A representation going to a power series ring over Zp that reduces or representation in Zp that reduces over this kind of picture that he might had in mind. And then he proved, in fact, that there's essentially, I may be forgetting some technical condition here, but I don't think so. Not variant. If you start with representation in, say, GL2 over finite field, for example, then there's always a universal deformation. There's a universal family over some p-adic ring, possibly something like the power series we had earlier, so that given any other deformation of your little representation, that in fact this guy is initial, it arises by pushing out from this universal representation by our ring homology. So that's what's kind of this universal deformation space for Galois representation. Now, the most important application exactly arose from this elliptic curve that I mentioned earlier, right? If you started out with an elliptic curve, well, initially you had this semi-stable condition, the singularity of the reduction from P. But in any case, if you look at the P torsion point of such an elliptic curve, you get a representation of G into GL to FP, right? Now, Mazur says that there's a universal deformation, that's that GL2 of R of it, right? But in fact, there's also something in the middle, and the study of this thing in the middle was what gave rise to an enormous amount of mathematics. What is that thing in the middle? Well, that T, you see, is a completion of a Hecke algebra of some sort, the kind of Hecke algebras that arise in the theory of modular forms. And the fact that you look at a representation into a ring parameterized by Hecke operators, right? This was this difficult work of Langlands and Tunnell. This was the modularity of mod P representations. So in fact, you're going back to this picture, you had a deformation parameterized by a Hecke algebra. But then because R is the universal deformation, you have a map from the top object to the middle. But then what was shown by Wiles and Taylor and Wiles was that under suitable conditions, this is not a bare universal deformation, there's a lot of arithmetic natural conditions. But they showed that R and T were in fact isomorphic. This map that comes from the construction of T and the universal property of R gives you an isomorphism. So the consequence, of course, was that in fact, if you look at this diagram whereby the p-adic representation of the curve coming from the p-adic phase module, then there's a map to that thing from the universal representation. But since they proved that GL2 of R is exactly the same as the representation associated to a Hecke algebra, then you get this kind of picture, this diagram at the bottom. And this is this famous theorem on the modularity of the p-adic representation. So this was Wiles's modularity theorem, out of which you get Fermat's theorem. And this all arose from the idea of studying suitable families of Taylor representations, right? And so I guess what I wanted to emphasize is that the ideas of gates here are ubiquitous in all this picture, although it might not be so obvious by the way number theorists usually talk about it. So I'll try to make it obvious by just giving you a very snapshot of the history that arose that gave rise to all these consequences in number theory. So first, there's this famous theorem paper of Wiles that appeared in 1995 on modular Rijksinstituut and Fermat's last theorem. And I just pointed out that this was heavily influenced by the paper of Mazur, Deformations of Taylor Representations. It came out in 1987. It was published in 1987. But there was a lot of a flurry of work, so to speak, right, surrounding that idea that was going on around at the same time. So there's a paper by Goldman and Wilson, for example, that was published a bit later. It was actually done earlier, so it's referred to as a very important source of inspiration in Mazur's paper. They study deformations of representations of fundamental groups of compact Kähler manifolds, so you get something that's more explicitly gauge theoretic in nature in the sense of somehow the constructions here heavily influence the category theory and the deformation theory that the present Mazur. But now there's a ton of work that I can't possibly do justice to that gave rise to the work of Goldman and Nielsen. So I'll just put in some highlights that came to me just in the middle of the night during the lecture, not as any serious representation, but hopefully not entirely unjust. So for example, there was the work of Atiyah on the Youngman's equation on Riemann surfaces, which I think inspired a lot of this moduli theory of representations of fundamental groups that came after it. They, in turn, refer very much to this a paper of Narasimhan and Seshadri on stable and unitary bundles on a compact Riemann surface from the 1960s. But what's interesting to me as a number theorist or an arithmetic geometer is that, in fact, a lot of these papers, especially the Atiyah paper and the Narasimhan and Seshadri paper, refer a great deal to this paper of Bay from the 1930s, Generalisation des fonctions abéliennes. So there, Bay is actually interested in the Mordell conjecture. So he's setting up this moduli theory, kind of a very old moduli theory of bundles on algebraic curves, as a possible approach to the Mordell conjecture on finite points on curves of Bayesian. So it's kind of interesting, as I said. I guess this is a slightly biased point of view, but I've presented a circle of history in such a way that starts with number theory and ends with number theory. But it's quite interesting that all this gauge theory plays a role inside this circle. So now I'll mention briefly another part of what I call pre-gauge theory, having to do with moduli of arithmetic principal bundles rather than just color representations, right? So what do I mean by this? So here, what we are doing, what one does, is study non-abelian cohomology. Right? So this is the cohomology of a topological group R, right? A non-abelian topological group R that admits a highly non-trivial action of one of these color groups. Then you can define non-abelian cohomology with coefficients in such a non-abelian group. Right? And so here it seems to be very useful, at least I found it very useful, to employ a gauge theory perspective, which maybe is not at all surprising. But I said at the beginning that this shouldn't be surprising. So reiterating that here. So let me be more, well, actually, let me skip this picture. So you don't have to look at this carefully, although I put down a bunch of lines, which may, too many lines crammed into a little half of a page, right? But the point is that in some sense, the idea that you should use cohomology of this sort in studying Diophantine geometry is very old, right? And it probably was studied most, given a serious application first in the theory of elliptic curves, where somehow you looked at cohomology with coefficients in the p torsion of the elliptic curve to say things about the Mordell-Weil group, the group of rational. Finally generated abelian group that's still the subject of very active research in number theory, right? Like, for example, conjecture of Rijksinstituut and Atiyah, roughly speaking, starts from this diagram. But this H1 with coefficient and EP, this is not a kind of a serious topological group, and it's also not non-abelian. It's the EP is abelian, not non-abelian, doesn't quite make sense. It's abelian. The more interesting thing, or more gauge theoretic thing, let's say, is where you try to generalize this picture to the case of a smooth projective curve of genus elite. So you can do this over any number of phases. You can also do it for other varieties as well, but for concrete, I stick to the simple case. Then point out that in fact that picture regarding elliptic curves, in order to generalize it to the study of other points and other varieties, in fact, what you have to do is you have to look at fundamental groups. You look at fundamental groups and homotopy classes of paths from one point to another. You fix a base point, and you look at homotopy classes of paths from B to X. Now, each of these are principal bundles for the fundamental group, because of course the fundamental group acts simply transitively on any of the path spaces, right? And you want to look at this as a function of the endpoint X. Right? And if this somehow is a generalization of Kummer theory, right? Maybe this is the only real contribution I've made to number theory ever, so I should emphasize the idea that this fundamental group theory and theory of paths is the first generalization of Kummer theory. You can't quite make arithmetic play a role if you just look at these discrete fundamental groups. So what you have to do is you have to start from this picture as the basic intuition, then complete the fundamental groups into various algebraic groups. This is a very well-known thing in Hodge theory and many aspects of geometry, where you know that fundamental groups don't just live as discrete groups, but you can complete them into algebraic groups. The most convenient one for our purposes is to complete it into a unipotent algebraic group. So there's an object called the QP pro-unipotent fundamental group of that curve based at the base point B. So I'm not going to give you a definition of this. There are many concrete ways to deal with this or to study this and look at its structure using the methods of rational homotopy theory in some form or another. Right? But here I'll just give you this very abstract description that it's the universal pro-algebraic pro-unipotent group defined over 2P that admits a homomorphism from this pi1. So that's the universal definition of such a thing. So if such a thing exists, it's completely canonical. You can believe that, therefore, right? However, in fact, you prove that it exists and say something about its structure. But the key fact for us is that when you construct, when you define and construct this pro-unipotent fundamental group, in fact, because of the fact that the curve is defined over Q and the base point is rational, right? This unipotent fundamental group admits an action of this Galois group. It admits a Galois symmetry that's not apparent when you just look at the discrete group. So that's the basic thing that allows you to apply this to number theory. So you can do this for the fundamental group itself, but you can also do it for the homotopy classes of paths. Okay? You take the path from B to X, and you can complete this by simply pushing out the principal pi1 bundle into a principal U bundle. So looking at the standard associated bundle construction occurs a lot in differential. You get a principal U bundle. But as I said, this varies with X, and everything inside admits an action of the Galois group. So what's the point of doing this is that, well, you can associate the points of the curve, the classes of the principal bundle of paths from B to X, right, to any point X. So that defines a principal bundle for U, so you get a non-abelian cohomology class associated to that point. And this can be used to study the structure of rational points. More precisely, you set up a diagram of this sort that takes the global rational points and puts them into a product of points over various completions. And there's a moduli space of principal bundle for these local Galois groups as well. And there's a diagram that allows you to, in some sense, sorry, is there a, I guess. So you see, this inclusion of the rational points into product of p-adic points or real points or things like that, this is very hard to study, but this becomes, the way we've set these things up, these actually become schemes defined over QP. They're really geometric objects. So you're replacing this inclusion by an inclusion of this. I didn't explain what they said, but there are also local conditions that are satisfied by this local principal bundles that come from points. That has to do with terminology of p-adic Hodge theory. So there's also a natural subspace that are just locally defined at each place P. So in fact, if you want to study the rational point, you're actually wanting to study the intersection of the image of this localization map of principal bundles and this subspace defined by p-adic Hodge theory. So there's a conjecture that in fact you can recover the rational points entirely via looking at this intersection of moduli space. So let me go back to the previous slide briefly again. So you look at the image of this localization map of principal bundle intersect with natural integral p-adic Hodge theoretic subspaces, and then you look at the inverse image of that inside the local point. So that should be exactly equal to the global point. So that's the conjecture. And but as I said, the point is that this thing here is completely algebraically defined. So this gives you a way of understanding how the global points of a curve is contained in type product of local. Okay. So the consequence is that you get, when you just look at the p-adic points of the curve, you get an analytic description of the way the global function points sit inside. So this is all conjectural, and this program works out rather explicitly in certain situations, but it's still quite hard work to make it work precisely. But nevertheless, when it does work, you get a collection of p-adic analytic functions defined on the p-adic point of the curve that cut out the global points. So that's the general strategy. What are these analytic points? So just to say a few words about it, what you have to do is construct a universal pro-unipotent bundle with connections on this set of p-adic points, right? And then look at the holonomy of this connection from your fixed points to various points x. And the holonomy matrix gives rise to various matrix coefficients and can form algebraic functions of those matrix coefficients. Evaluate those and the p-adic points to get analytic functions that cut out the global points. So I'm telling you just little bits of detail here and there without going into any detail, just to give you a sense that ideas of gauge theory are sort of ubiquitous in this approach. Right. So I don't have that much time now. So let me finish now, more or less, by describing finally gauge theory itself, right, rather than what I described as pre-gauge theory. Any physicist will tell you that just looking at these moduli spaces really isn't gauge theory. You have to have these moduli spaces. You have to have spaces of principal bundles with connections and things like that, but there also has to be an action. Right? So these things are defined by various actions, like the actions that give rise to Maxwell's equations or more general Young's equations. Like that, right? And it turns out that you do have actions, or at least baby versions of what should be the really geometric actions, even in these pairs. So yeah, I'll just give you a few examples to just give you a flavor of the kind of actions that arise. Actually, so maybe I will skip these slides because I may have time to return to it later. I'll go to the examples first and tell you the motivation later. So the simplest kind of actions is what you might call an arithmetic Chern-Simons action. Okay? So how does this work? The basic facts that you need for this is that when you start out with the spectrum of the ring of integers of an algebraic number field, then H3, the third homology of such an object GM, is isomorphic to Q mod Z. So GM coefficient you should think of as being like the S1 coefficient you see in three-dimensional Chern-Simons theory. And if you do that in Chern-Simons theory, that will just be S1, right? You will get S1 as that's a homology. Here you get Q mod Z. So somehow that's a discretized version of S1 that you get because of the arithmetic nature of theory. The homology theory here, you have to take one of these exotic homologies called cut homology, so you don't have to worry too much about the definitions of such things, but just take it for granted that this works in many ways, like topological homology that you're used to. So using this, if your field happens to contain an nth root of unity, right, then the group of nth root of unity, that's what I call U, and there is actually just isomorphic to Z mod n. I wrote that as 1 over nz mod z because that's the way to view it as a subgroup of Q mod z. So that becomes isomorphic to the group of nth roots of unity via the exponential map, but meaning together with the Galois action, because if it contains an nth root of unity like this, the Galois action is trivial, right? So that H3 with coefficients in Z mod n is also just Z mod n via the same invariant technology. Using this, you can set up a map from H3 with coefficients in Z mod n. Sorry, this is group homology. This is for the fundamental group of it. That will map to the fundamental group to H3 of the schemax, which then is isomorphic to Z mod n. So you just get a map from H3, the group homology of pi1 to Z mod n, which you know as invariant. That's what the terminology. Now, suppose you start out with a finite group R, right, and you fix a homology class C. So this is just a discrete homology class coming from a finite group R. So this is similar to what in Chern-Simons theory people would call a level. Right? Then using this, you get a function on a very simple moduli space of Galois representations. And suppose you had a representation from pi1 to this group R. Right? It might be GL2 over FP or some simple group like that. These are the examples in mind. If you do that, then you get a Z mod n valued function. Why? You can take a homomorphism like this, pull back this homology class to get a homology class for pi1, right, and apply the previous invariance. So in other words, the value of a homomorphism on this class after applying invariance is the function of the homomorphism. So you get a function out. So this is the kind of an arithmetic discrete or finite Chern-Simons functional that you get on a very simple class of Galois representation. Now, there's also something called an arithmetic BF functional. The reason for the terminology BF, I won't go into that, the physics thing that arose in an attempt to find topological quantum field theories defined in any dimension. But in this arithmetic setting, we have a version that's again very simple, except here it goes from product of two spaces. H1 with coefficients in Z mod n, product H1 with coefficients in the root of unity. You can use the box sign operator associated to an extension like this to get a map from H1 to H2, which then you can take a product with H1 that gives you an H3 class, which then, as we said, because of this formula involving class homology, gives you a Z mod n valued function on this product. So that's a simple version of an arithmetic BF function. You can do this with abelian varieties as well. Right? You can take one abelian variety A, a dual abelian variety, and you have to put some technical conditions to make this work in a simple-minded way. You can generalize this to without the conditions, but then the formula is more complicated. But starting with that, you get a function on, again, a product, H1 with coefficients in the nth version of the neuron model of one abelian variety, plus H1 coefficient with coefficients in the nth version of the other abelian variety. Again, taking values in Z mod n, using a box sign operator and cup product and the invariant. So this is again a version of the BF function. By the way, I should say, so there are many things that are called BF functions in topological quantum field theory, but typically they look like functions of I form cross n minus I form, where n is the dimension of the manifold. So this is a version of it set up in this arithmetic over this number field, various coefficients of a dual nature to each other. So what I wanted to do is give you a flavor of a quantum theory associated to these functions, right? And then try to tie this together with the theme that I tried to articulate at the beginning about index theory and region of unity in mathematics, but to the extent that I'm able. this is just a little bit of what it means, what it would mean to quantize the theory I described on the previous slide. So what does one do? So for example, you have this Chern-Simons invariant defined a moduli space of Galois representations for a finite group R, right? So there are only finitely many such things. So you can take exponential of such a function and then sum over representation. So you can see this is a very much a baby version of what physicists would call a path integral, where the fields are these Galois representations. You take the exponential of the value of the function on the field and then sum over the field. So this is an example of a quantum version of the theory. Right? So here's a formula. So here's this is a very simple case where R is just Z mod P, and you have to make some extra assumptions on the box sign operator for the formula to come out simply. Otherwise, it just becomes more complicated. So this is joint work with a collection of people. What happens when you compute a formula like this? So here's what you get. So this formula, this sum, in the case of the simple group Z mod P, turns out to capture a sort of, let's say, important arithmetic invariant. Like this is the class number, the P part of the class number of F. So this is the ideal class group of F, and then you're looking at the P portion subgroup. Look at the number of elements in it and take its square root. That's this quantity here. So the rest of this, the stuff here, this is a power of I of some sort. This is just a sign, it's a Legendre symbol. But inside the Legendre symbol, you get the determinant of this operator, which is quite familiar, I think, to people who do path integrals in quantum field theory. Except it's slightly odd because this determinant is an operator that goes from a vector space to some other vector space. Right? This other vector space is actually the dual of the first one, if you use duality theory in arithmetic homology theory. So what you'll know is that if you have an operator going from a vector space to its dual, this determinant is not well defined, but it's well defined modulo squares. Right? So when you put it inside the Legendre symbol like this, the square dependence goes away. So you get an interesting kind of determinant, which is perfectly well defined. That's the formula that you get when you do this path integral using for the Chern-Simons function. What happens when you do this for this PF function on the product of Zn coefficients and Un coefficients, you get a similar kind of formula, except the class number that just occurs directly, not with a square root, right? Because you are doubling the fields here somehow. You get directly the class number rather than square root. And this is the units inside your field, right? Inside the ring of integers modulo. So for technical reasons, you have to take n sufficiently large. Again, you can do this for any n except the formula becomes slightly more complicated. And when you do this for this abelian varieties and put the BF function on the abelian varieties, then again you get something similar, except for what's involved here is the Mordell-Weil group of two abelian varieties, and then the tetra-Kreyvich group of one of them. It doesn't matter actually. This you'll get the same answer if you use P. But anyways, you get the kind of natural invariant that people study in a number of different contexts in number theory. In fact, that was the slide. These were the slides I skipped at the beginning. That in fact, in some sense, one of the goals that I would have is a bit of a speculation to understand another class of actions, which are called L functions. The L functions are very classical objective numbers here. They're subject to many conjectures, right? But they should be viewed as actions of Galois representation. So that's a point of view which I think is a serious one. That somehow what you're trying to do when you're studying L function is you start with a Galois representation and you set up an infinite product like this. This infinite product usually diverges, well, not usually, but often diverges. So the goal, one of the goals of the theory of L functions is to figure out how to define this infinite product correctly. And it's not easy. So one standard approach is to twist it by some complex number like this. Yeah? Take the number of elements inside the residue field associated with the place and raise to the minus s power. Then you can prove that for natural representation, this does converge for real parts sufficiently large, and you'd like to define its value at s equals 0 by analytic continuation. And the idea that it should be possible to do this is called the Hasse-Weyl conjecture. In fact, you should be able to define this infinite product via analytic continuation. But there's a kind of speculative thought that formulas of this sort or definitions of this sort should be able to make use of some ideas from physics. And that's also suggested by some of these formulas that you see in either theorems or conjectures involving special values of this. This thing here is called the BSD conjecture. What's up here is called the class number formula. What you find is special values or leading orders of these cell functions at 0 when they're well defined, when you can define them, actually can be expressed in terms of natural determinant and other natural arithmetic variables. So this is the subject of an enormous industry of work in arithmetic geometry. But so I'll conclude by pointing out my main speculation of the day. Relatively complete formulas functions here. As usual, I prepared much too many slides. But anyway, so here's the concluding speculation. It's that this very local index theorem that I mentioned at the beginning, right, should be quite analogous to these path integrals in arithmetic geometry, formulas that I showed you earlier, where a path integral gives you a determinant of some sort. And so it should also be very analogous to conjectures from formulas and values of L functions. And this may seem very quixotic, but nevertheless, there are a number of reasons to think so. So here, remember, this local, very local index theorem involves identifying a determinant with local intersection. So there's, in principle, a sum over places that occur here, similar to the product over places that occur inside the definition of an element, for example. By the way, we always forget this kind of thing, but this is also an object that's potentially infinite. We know, you can see it because there are self-intersecting numbers up here. We know how to make those finite by moving the divisors that support these, that define these line bundles, right? So we know how to make this finite, but through a lot of work, it turned out that actually these are also potentially infinite. We've changed them into finite quantities, and then you can prove that it's equal to a determinant of this sort. So somehow, this arithmetic gauge theoretic path integrals, as well as conjectured formulas for L functions, I believe, are quite analogous to these local index theorems. Now, some of you may be reminded of this joke, right? Because somebody was supposed to be giving a talk on combinatorics, right? And in the audience, maybe Kazdan or somebody like that. It wasn't Kazdan. Somebody in the audience gets up, who's been sleeping through the whole lecture, gets up and says, well, okay, so this is just like the Rijksinstituut theorem. The person, the lecturer, is astounded. Maybe this person has some enormous insight that was missed by the computations that he was doing, right? But then the person comes up to the board and says, it says A equals B, therefore it's like the Rijksinstituut. So this analogy might remind you of that joke, right? So I take it a bit more seriously than that, but of course you're free to view it in the same light. Thank you very much.
Thank you. That was a most interesting set of analogies, results, speculations, marvelous. So questions, comments, either in the auditorium here or again via the chat. Perhaps while people are collecting their thoughts. Yeah, did I hear you correctly? You were suggesting, speculating that the L functions you wrote down are like actions?
They should be like, that's right. So those should be like roughly like path integrals.
Oh, so they're not actions themselves?
No, no.
Okay.
I have a question. with these formulas for the class numbers that you wrote down before with the square root, for example, do you have examples where you can compute some class numbers in a nicer way than before? Or?
So that's actually, yeah, no, that's a good point. The short answer is no. This doesn't seem to quite give you computationally useful from me. It would have been, you see, it is suggestive that it should tell you something about class numbers because I find it, it's very suggestive because if you look at this formula, yeah, so as you say, there's this class number occurs here. And what's this thing that we're computing? It's what people call an exponential sum. It's a sum of exponentials and some rational numbers over here. So in fact, the fact that, and this is just some science and powers away. So this, for example, what I thought would be, it would be nice to use this formula to get bounds on class numbers. Maybe I just haven't thought hard enough, but it didn't seem to be so easy to actually use it. But it's a tantalizing question.
There's a question, I think, coming through the chat.
Peter Sanak wants to ask a question.
Hi.
Hi.
Thanks for a very nice talk. I have a question about your speculations. So in the number field case, you ended with the Hathaway L function. And as far as I know, unlike the function field case, you cannot, or we don't have any scheme or dream of analytically continuing such a function without the use of modular forms. So modular forms somehow are indispensable. Is your do your speculations allow you, even in a dream world, to avoid modular forms, automorphic forms?
I'll try to tell you my honest answer. Yes, that is a dream of some sort. It's rather the other way around. I was hoping that speculating about these path integrals in a sufficiently hard way might make the automorphic forms also arise naturally. Okay? Rather than, I don't know your perspective, but maybe it's simply because I'm naive. But even if you look at the modular form or automorphic form approach to analytically continuing L functions, right? It's a bit magical, right?
Yeah, I mean, I have a very strong opinion that if we lived only in the function field world, we would not have this reliance on modular automorphic forms, Langland's program. It would, because you can do it by growth index machinery directly.
Right.
And in the number field case, I think it's indispensable in any way I can think about it. And I was curious where they come into your picture, or maybe they don't. That would be quite remarkable. Anyway,
no, I agree. I hope that, in a way, I hope for both things that maybe they won't come into the picture, but maybe they will arise naturally. Because actually, so what is your opinion about that? I'm quite curious. The Langland's program, as it still is rather magical, isn't it? I mean, the fact that they would become automorphic, is there a kind of motivation for it, right?
Yeah, somebody needs to write the paper that maybe Atiyah would have enjoyed, the unreasonable effectiveness of automorphic forms.
You should write that paper. I'm happy to help you.
All right, okay, thanks.
Yeah, thanks for your comment.
Okay, well, splendid. I suggest that we draw questions and comments to a conclusion there, and that we thank Minhyong again. There is tea and coffee, or at least tea available. So back at 4 o'clock, I believe.